This video explores the topic of sensor fusion within the framework of the European project titled Personalized Education in Measurement Science and Technology Empowered by Machine Learning. Sensor fusion is the process of combining data from multiple sensors to achieve more accurate and reliable information than any single sensor can provide. Modern systems use multi-sensor architectures where different sensing modalities, such as inertial, optical, and environmental sensors, work together through a shared data acquisition and communication framework. We briefly introduced the main fusion levels: data level fusion for merging raw signals, feature level fusion for combining extracted information, and decision level fusion for integrating algorithm outputs. These concepts connect to common architectures like centralized, distributed, and hybrid fusion systems. Examples from robotics, autonomous vehicles, smart IoT devices, and industrial monitoring show how sensor fusion improves accuracy, robustness, and decision-making, supporting the goals of PEMS-ML and building a strong foundation in modern measurement science. Sensor fusion is the process of combining data from multiple sensors to produce a clearer, more accurate, and more reliable understanding of the environment. Instead of relying on a single measurement, modern systems merge information from cameras, LiDAR, radar, inertial units, or environmental sensors to reduce uncertainty and improve perception. This is crucial in autonomous vehicles, robotics, industrial automation, and smart IoT systems, where different sensing modalities complement each other. Advances in AI, IoT, and edge computing now allow fusion to happen faster and closer to the source, enabling real-time monitoring, navigation, control, and predictive analytics. As the saying goes, in the world of sensing, one sensor sees the forest, another sees the trees. Sensor fusion sees the ecosystem. This holistic view is what makes sensor fusion a cornerstone of modern intelligent systems. Sensor fusion brings major benefits that make modern systems more accurate, robust, and intelligent. It improves accuracy by reducing noise and combining different sensing perspectives, resulting in cleaner and more reliable information, especially in environments where signals are uncertain or affected by disturbances. It also increases robustness. If one sensor becomes unreliable or fails, others can compensate, ensuring continuous operation in safety-critical areas like autonomous driving, robotics, and industrial automation. Another key advantage is deeper contextual understanding. By merging visual, motion, environmental, or location data, systems can better recognize patterns, anticipate changes, and make more informed decisions. Finally, sensor fusion enables real-time responsiveness. Synchronizing and processing data efficiently, it supports fast navigation, tracking, and monitoring in dynamic environments. Together, these strengths make sensor fusion a core technology for the next generation of intelligent, AI-enhanced measurement systems. Each sensor provides only part of the information. Some give visuals, others depth, motion, or environmental data, but each has its own noise and limitations. Sensor fusion combines these imperfect signals using statistical or AI-based methods to create a more complete and reliable estimate of what is being measured. Key techniques include weighted averaging, where more accurate sensors influence the result more; Kalman filtering, which merges predictions and measurements in real time; Bayesian inference, which updates beliefs as new data arrives; and machine learning approaches that learn optimal fusion rules from experience. Together, these methods reduce uncertainty and significantly improve accuracy in modern intelligent systems.
Sensor fusion is a core enabler of modern intelligent systems because it combines the strengths of multiple sensors to create a far more accurate and reliable understanding of the environment. In autonomous vehicles, fusing camera, LiDAR, radar, and GPS data produces a robust world model that supports safe navigation, even in challenging conditions. Drones and mobile robots rely on fusion of IMU, magnetometer, GPS, and vision to maintain stable flight and precise localization, allowing them to operate even when one sensor becomes unreliable, such as temporary GPS loss. In industrial automation, merging information from temperature, pressure, vibration, and vision systems improves process control and early fault detection. Everyday devices like smartphones and wearables also depend on fusion, combining accelerometer, gyroscope, and magnetometer signals for orientation, or heart rate and motion data for accurate activity and health monitoring. The key advantage across all these domains is enhanced accuracy, robustness, and redundancy. Fusion reduces noise, resolves sensor weaknesses, and ensures systems can still function under sensor failures or harsh conditions. Ultimately, it provides the complete situational awareness required for reliable real-time decision-making in fast and dynamic environments.
Sensor fusion architectures can be organized in several ways depending on processing needs, communication limits, and system design. In centralized fusion, all raw sensor data is sent to one fusion center. This gives the most complete information but requires high bandwidth and creates a single point of failure. In decentralized fusion, each sensor or module performs local preprocessing, and only refined results are transmitted. This reduces communication load, scales better, and improves fault isolation, making it common in robotics and automotive systems. In distributed fusion, there is no central node. Instead, agents share information peer-to-peer. This makes the system highly robust and suitable for multi-robot teams and large IoT networks, though it is more complex and sensitive to communication delays. Data-level fusion combines raw signals such as IMU data, LiDAR clouds, or stereo images. It preserves the most information but requires tight synchronization and high bandwidth. Feature-level fusion merges extracted descriptors like key points, object lists, or tracks, reducing data size and improving robustness, but some detail is lost during pre-processing. Decision-level fusion integrates final outputs from separate subsystems using voting or rule-based strategies. It is simple, modular, and easy to implement, although it provides the least detail. Sensor fusion uses several key techniques to combine information and reduce uncertainty. The Kalman filter provides optimal real-time estimation for linear systems with Gaussian noise, while the extended Kalman filter, EKF, adapts this idea to nonlinear models by locally linearizing the system. For highly nonlinear dynamics or non-Gaussian noise, the particle filter uses many weighted samples to approximate the full probability distribution. In parallel, neural networks and AI-based fusion learn patterns directly from data, making them effective in complex high-dimensional environments where traditional models struggle. These methods often complement each other. Engineers frequently combine filters with AI to achieve the right balance of accuracy, robustness, and computational efficiency. As sensing systems grow more complex, such hybrid fusion approaches are becoming essential for safe and adaptive decision-making. Sensor fusion plays a crucial role across many real-world applications, and two of the most impactful areas are autonomous vehicles and healthcare. In autonomous driving, vehicles rely on a combination of GPS, inertial sensors, LiDAR, radar, and cameras to understand their surroundings. Each of these sensors captures different aspects of the environment: position, motion, depth, and visual detail. By fusing their outputs, the vehicle can localize itself accurately, detect obstacles, interpret the road, and make safe decisions even in challenging conditions such as darkness, fog, or sensor interference. This fusion backbone is what enables reliable navigation, lane tracking, and collision avoidance. In healthcare, sensor fusion supports smarter and more continuous patient monitoring. Systems combine ECG signals with temperature sensors, motion detectors, and wearable physiological monitors to build a richer picture of a patient's health status. While a single sensor may capture only one physiological parameter, fused data can reveal patterns such as arrhythmias combined with physical activity, early signs of infection, or abnormal vital sign correlations. This enables more accurate diagnostics, earlier detection of medical issues, and personalized healthcare interventions. Together, these application areas demonstrate how sensor fusion enhances safety, precision, and intelligence in systems that interact directly with human lives. Every day, smartphones and wearables rely heavily on sensor fusion as well. Accelerometers, gyroscopes, magnetometers, GPS, and optical sensors work together to enable accurate orientation tracking, step counting, activity recognition, and seamless location-based services. Fusion makes these devices more responsive and energy efficient. In robotics, sensor fusion is essential for perception, mapping, and control. Robots integrate data from cameras, depth sensors, force sensors, and IMUs to understand their surroundings, balance, grasp objects, and navigate complex spaces. This multi-sensor approach improves stability, precision, and autonomy. Environmental monitoring relies heavily on sensor fusion to create a more accurate and reliable picture of outdoor and indoor conditions. Individual sensors, such as air quality modules, particulate counters, gas sensors, humidity probes, or weather instruments, each capture only part of the environment and often produce noisy or fluctuating data. By combining these signals, sensor fusion reduces uncertainty and improves the detection of pollution peaks, temperature changes, and harmful gas concentrations. Fusion also enables systems to track environmental patterns over time, correlate information from multiple locations, and respond more intelligently to dynamic conditions such as smog events, wildfire smoke, or rapid weather shifts. This approach supports smarter decision-making in air quality networks, smart city platforms, climate research, and health-oriented applications. Ultimately, sensor fusion provides a more complete understanding of the environment, enabling more accurate forecasting and better protection of public health. Thank you for your attention. This video was produced through the collaboration of SS Cyril and Methodius University of Skopje, the University of Niš and Politecnico di Milano, within the framework of the European project Personalized Education in Measurement Science and Technology Empowered by Machine Learning. More information about the project can be found on the project website and LinkedIn page.